Just a little information, so how you're aware. One, our projector's working again, so yay. But I'm going to go to this page. So the funny thing with teaching is, I always joke like this. When someone says, "Hey, you're not really teaching," I'll just say, "Well, can you watch my video and tell me what I'm doing then?" That's kind of my defense. I will tell you from our last test, we did a pre-test and a post-test. They were both done on Schoology. Okay? So I'm going raw statistics for you. So I did something called a two-sample t-test. I paired up your pre-test score and your post-test score. If you didn't take the pre-test, I didn't include your post-test score. If you didn't take the post-test, I didn't include your pre-test score. Okay, so it's called two-sample t-test. My t-score, because I subtracted the pre-test from the post-test, it's going to be negative, was negative 12.6. My R value, not my R value, my p-score was that. Okay? So what this means is I compared what you did originally on the pre-test to what you scored on the post-test. Now, I had two students that I untaught stuff to, meaning they did worse on the post-test than they did on the pre-test, while all my other students did much better, ranging from, I had some kids that got 0.88 on the pre-test first score, so 0.88, and then that same person earned like a 14.67 out of 15 on the post-test, which shows they learned. So what does this mean? I'm not worried about telling you about what the t-score is at this point, but the p-score means this. So if your p-value is less than 0.01, your p-value is less than 0.01, means that your data is significantly valid. Being my p-score is this, which is much smaller than that, means if I were to repeat everything the exact same that I had done, given a pretest, gave the same lectures, gave the same tests and quizzes, gave the same homework, gave the same post-test, if I were to do that 1 out of every 1 million times I do it, I would show different results. Is that good or bad? So if I were to redo everything I had done, so just think about this as far as numbers. 1 out of a million. If I were to do everything the exact same time of the year, same time everywhere, my results show that only 1 time out of a million will my results be different. What did my results show? Pretty simple. Yeah. So that's kind of the stuff where a lot of times it's real easy if you are not a classroom teacher. If you do any other job, it's real easy to say, "Oh, the schools aren't doing their job." Okay, people say that a lot. People say, "Oh, these kids aren't being prepared for real life." Really? I don't know what's going on in their classrooms, but I'm pretty sure you guys are being prepared. So now, because of you being a part of my class, you are part of the 999,999 out of a million that learned. Good job.
What about that one person?
Out of the million, I'm not worried about them. That person can die. I'll just say that. Just because I'll only teach about 17,000 students in my career, so I won't get to a million. So they're safe.
So many.
1 out of a million. That's 5 people in this state. Now, how significant is that?
And they all go.
That's good. So, all right, let's take a look at our notes. Let's take a look at our notes. We ready? You set? So let's start learning this stuff. I can graph quadratic functions by finding 4 points of interest and using a table to plot 5 values. Okay, sounds good. Okay, graph the following. Is the first one a straight line? How do we know it's a straight line? It doesn't have an exponent attached to the x. So this first one would have a y-intercept of -5, so 1, 2, 3, 4, 5, and a slope up to right 1, and it looks like that. The second one, we could use the cover method. It's a straight line. If I do the cover method, if I cover the y value, it crosses the x at 4, covers the y at 3. Okay, that's cover method, first semester. This one was point slope, so this tells me that I have a point at 4, -1, because you do opposite here and here. So 4, -1, and I have a slope of down 3, right 1. Okay, so these are linear. These are straight lines. I know they don't look too straight, but just go with me. We good? This is all prior knowledge. This is stuff we've seen before. Okay, yes, I could give you a review unit on it, which I probably will come before the final. So if we put this on the final, you'll be like, oh yeah, that's right, I remember doing that. Okay, of all the methods, this is the most common. This one's the next common, and this is the one that we don't see all that often, so sometimes it goofs us up when we see it. But it makes you normal. All right, so the quadratic equation, the general form is ax squared plus bx plus c, where a is a number that's attached to the x squared term, that's called the quadratic term. B is attached to the x term, which is called the linear term. And c is just whatever the number is at the end. That doesn't have an x attached to it, it's called the constant. We okay? Yes. So a parabola has a few important components. So the vertex is either the bottom or the top of the graph itself. It depends if it opens up or down. We won't deal with parabolas that open sideways in this class. The axis of symmetry, which is the line that acts like a mirror that you can fold it over on top of itself, and it's symmetric about on either side. The y-intercept is where we cross the y-axis. And then the roots are the points where the parabola crosses the x-axis. So where our y value is 0. Now, do you think all parabolas would need to cross the x-axis? So here's what a traditional parabola looks like. Crosses the x-axis twice. Do you think I can have a parabola that looks like that? Does that blue parabola cross the x-axis? So this is definitely means something. Okay, and we'll talk about it more. Is it possible, do you think, that I could have, let's do this one green, a parabola that comes down and kisses the x-axis one time? Yep. Yeah. Absolutely, and that means something else. But we're going to talk about these things. And then we could flip all these upside down. We could have parabolas doing this. You know, they can flip upside down as well, and that's all fine. And again, we're not talking about the sideways parabolas because that's not part of this course.
So every time it crosses the line,
No. If the starting point and the end point are at the same direction. So they're both going up or they're both going down. That's a parabola. It has one turning point in it. It changes from going down to going up. Or going up to going down. Okay? So places, just so you know, where you will see parabolas in the real world. If you throw an object, it is on a parabolic arc. If you jumped off of a high dive, because we're coming up on summer, at the swimming pool, you go jump into the pool, the acceleration that you accelerate towards the water is a parabolic function. If you drop something off of the top of a house or a building and it falls to the ground, it accelerates by a second degree, which is a quadratic. If you've been in a car and the brakes have been applied, that is a parabolic function of how it works. Okay? These are all things that happen in math. You go out to the water fountain. I'm not talking the one that dumps from the top into your bottle, but the old school one where you have to bend over and it kind of has this, this little arc going. That water is following a parabolic arc for you. Okay? The higher the pressure, the higher the arc. The lower the pressure, the more the person has to French kiss the spigot to get the water out. Okay? Meaning they're putting their mouth on it, and then you're like, I think I'll find another water fountain. Right? There's always that one kid in elementary school you're watching, you're like, I'm going to throw up.
That's so gross. Remember to do that all the time.
All right. So this is a parabola that opens up. This is a parabola that opens up. Does everyone understand why I say it opens up?
Yeah.
Is there any part of my saying that? They're like, how do you know it opens up? Okay? So, it's a parabola that opens up. That's all it is. It does seem to cross the x-axis. It does seem to cross the x-axis is here and here. Crosses the y-axis here. It opens up. There's a line that's right here that makes a symmetric thing where if I were to fold this over, it would fold on top of itself. Yeah.
Yeah, I was just about to say that. Basically
Mirror image, yeah. And that's a big part of it. I have some cool things that we're going to show on how these really work and where it really applies. And I think you'll enjoy this unit. I think it's going to set, like, even if you do it that pretest, you're like, dude, boom, forget it. You're going to nail it. I really feel comfortable with it. We plan on being done, I think April 20th will be our test on this unit.
Okay.
Yeah, so it's a while. We got spring break in the middle of it.
That's in a month and 4 days.
Okay.
Hey, spring
Oh,
break.
wait.
This-
14.
Not next week, the week after.
All
All right. Yeah.
5 school days.
What?
25th of May.
All right. So A falls right there. Agreed? This tells us if the parabola opens up. If it's positive, the parabola opens up. So if it's positive, if A is positive, so greater than 0 or positive, the parabola opens up, just like this picture shows, but I'll draw one in there. If it's negative, meaning that, your parabola opens down. Doesn't matter what all the rest of the signs are doing. The very front sign, the A value, dictates whether it opens up or down. Okay? The vertex can be found using this little equation, x equals negative b over 2a. Well, let's see, negative b, our b value's there, over 2a, our a value's there. Okay, this is going to find us the x component of our vertex. And we're going to work with this a lot. So, like, I'm going to move on the screen. Don't worry, we're going to be working with this. The y-intercept can be found wherever you plug zeros in for your x values. So your y-intercept is basically y equals c. So this is your 0, comma c would be where it crosses every time. The roots can be found when you have 0 is equal to ax squared plus bx plus c, where you might have to factor this. You might have to recognize there's a difference of 2 squares, but you set it equal to 0. So that was the very last part of our chapter. And then the axis of symmetry. Anybody see where the axis of symmetry is used different up there? Is that equation used twice? Take a look up there. Where does it go? Yeah, it's related to the vertex. So as soon as you find the x component of the vertex, you've actually found the axis of symmetry, which is a vertical line that goes right through the x component of the vertex. Okay, so there's not a lot of information there. People try and make parabolas to be a very complex item. They're actually a pretty beautiful thing. You'll enjoy it. All right, what do we got here? Okay. Graphing quadratic. So this is just giving us, find the x-coordinate of the vertex using negative b over 2a. So this is just our directions. We'll go with this. We're going to draw on the axis of symmetry, which is a vertical line that goes through the x component. We make a table of values to the right and to the left of the vertex. We do that because it's a mirror image. Okay? And we find the y-intercept and other point if it's reflection if possible. Meaning the y-intercept might take place here, but there might be another point that has the same y value over here on the other side of the parabola. Plot the points and connect with a smooth curve from the parabola. Find the roots if possible. The roots are where they cross the x-axis. You can't always find the exact value for the root. If it factors, you'll find the exact values, even if it's a fraction. If it doesn't factor, then it's got an irrational answer. And an irrational answer, if you remember, if we go back, is where we can't take that decimal that's 1,000,000 miles long. We can't figure out the fraction that it goes with it. Okay, you find out about where it falls, but not exactly. Okay, so let's try this. We're going to walk through real slow. Okay? The first step was to do what? It was on the last page. Find the x-coordinate. So I'm going to do that by using x equals negative b over 2a. Okay? So looking at my equation right here. Looking at my equation right here. What does my a value appear to be? What is my a value? What? It's the number before x squared. What's the number before it? What's the number before x squared? 1. Good. So there's a 1 right here. What's my b value appear to be? 2. What does my c value appear to be?
3.
Close. Negative 3. Okay, that's my a's, b's, and c's. Do I have enough information from those a's, b's, and c's to plug into this value right here?
Wait,
I need a negative b over a 2a. Do I have an a? Do I have an a? And a b?
Yeah.
I do. So ready? So that negative comes along. Negative. That's an equal sign. Negative. My b value is what? 2. Negative 2 over 2 times, what's my a value?
2.
1. Okay, do the math. Negative 2 and over 2 times 1, that's over 2. So I get x equals negative 1. Where did negative 1 just come from? Yeah, you had 2 over 2. It reduced it. It was negative 2 over 2, so I reduced that. So this is my axis of symmetry. It's also the x component of my vertex. So let me just pause there a minute. Okay, so I gained my axis of symmetry by going x equals negative b over 2a. It also finds me my x component of my vertex. So I want to draw in my axis of symmetry, and I'll do it. Let's do this. We'll go that. We'll go with a green. So x equals negative 1 is a vertical line. Right there. I use the straight edge. I use the straight tool. Okay, so that neon green is called our axis of symmetry. That's the line that we fold over. It acts like a mirror of our parabola. Now, on the axis of symmetry, you always have your vertex. Your vertex is either your lowest point if the parabola opens up, or your highest point if the parabola opens down. So we need to start thinking about how we can go through this problem. Okay? So I'm going to put my vertex right here in the middle. Okay? Because the vertex is symmetric. How do you think I might find my y component of my vertex? plug it in. You're going to plug it in. It's an x value, right? So that's an x value right here. If I take that x value and plug it in there, I get 1 squared, or negative 1 squared, excuse me, right? Plus 2 times negative 1 minus 3. Agree? Does that make sense?
Wait, how do you know where to put it on the X part? Why'd you put it like right in the middle?
Are you on the purple? Or what are you looking at?
Yeah, the purple, like the -1 on the X.
So it's symmetric. So we're going to graph on either side of the vertex. What's nice is if I find this point will be the same as long as it's the same distance from it.
Okay.
Okay? All right, so -1 quantity squared. What's -1 times -1? It's positive 1. What is 2 times -1? -2 minus 3. So 1 plus -2, so that's 1 minus 2 minus 3. What's 1 minus 2? What's 1 minus 2? -1. Whoa, what happened? Where'd I go? So 1 minus 2 is -1. What's -1 minus 3? No, you said it. -4. So at -1, -4, -1, 1, 2, 3, 4, there's my vertex. Hey, just by looking at this, is my parabola going to open up or down? It opens up. Why? What value is positive? A, B, or C? My A value is positive. I have a positive 1 in front of x squared, right? That tells me it's going to open up. Okay, so now, let's figure out a little bit more. If I were to go one number this way, I get to 0. Agreed? If I go one number this way, I get to -2. Agreed? What appears to be an easier number to plug into our equation to get the y component? Because it'll be the exact same. 0? Okay, so if I plug 0 in, I get 0 squared, which is 0. 2 times 0, which is 0, minus 3. Well, I guess I can put the -4 down there. So, and that's going to give me the same value. So I have 2 more points. So I have -2, -3, and 0, -3. Right? So I'm going to pick one more value this way. So we'll pick 1, and I'll pick -3. So I picked a value to the right of that and a value to the left of that. Does 1 appear to be easier to plug into this than -3? Yeah, they're going to give me the same value. So what's 1 squared? 1 plus 2 times 1 minus 3. 1 plus 2 is? 3 minus 3 is? Oh, cool. So I get 1 comma 0 right there. -3 comma 0 right there. Can anyone see how this parabola is going to start looking? Open it up and down?
Oh, I see.
It either opens up or it opens down. The A value will tell you if it opens down. Nope, they will always be open. Parabolas open up or they open down. Cool? All right. So, are we able to see where it crosses the y-axis? Can we see where it crosses the y-axis? Can we see where it crosses right here? Where does it do that? At 0, comma what? Right there. -3. At 0, 3, right here is where it crosses, right? Now, does it appear we know where it crosses the x-axis exactly? What do you think? Do we know exactly where it crosses the x-axis? Take a look at our graph. If it crosses the x-axis means our y value is 0. Do I have any y values up there that are 0 on my grid?
Yes.
I do have 2 of them. Okay? So my roots are -3, 0 and 1, 0. There's my roots. It worked out real nice and neat that it crossed there. If I were to have factored this polynomial, it's quadratic. It would have factored down to x minus 3, x plus 1. If I would have factored that down, this would have factored to x minus 3 and x plus 1. If I would have factored that originally, which we just covered in the last chapter. If I were to set these equal to 0 to solve, I get x equals what? Oh, actually, I made that backwards. Plus, minus. I just taught the factoring unit, and I can't remember how to factor. X equals -3. Boom, boom, boom. X equals x equals positive 1. Boom, boom. It's all there. All right, so let's go back and let's walk through this. So the a value, the value that's sitting right in front of the x squared, sometimes you can't see it because it's a 1. We don't go 1x squared. That a value tells us, does it open up or down? If it's a is positive, it opens up. A is negative, it opens down. The a value is in front of our x squared, which is called our quadratic term. The b value is attached to the x value, which is called the linear term. The c value doesn't have a letter associated with it. It's a number only, which is called the constant. The a, b, and c's are used on this problem. I have a general equation called x equals -b over 2a, which finds us 2 things. It finds us the axis of symmetry, which is the mirror, where it would be symmetric about it. And it also finds us the x component of the vertex. The x component of the vertex, we can find the y component of the vertex by plugging that x value back into the original equation. We find the y value, just substituting in. Okay, let's see if we can walk through this right here. We good? All right. Item 1, just things you notice right off the bat. Take a look at it. Will this parabola open up or down, and why?
Down.
Down. Why?
Negative.
Because it's
What's negative?
The
The a value is negative. It opens down. Okay, so let's just for the heck of it, my a value is -2, my b value is 8, my c value is -2. Does everyone feel comfortable with how I just did that? Because that a value is negative, this parabola is going downward. This might not be the best time to go to the restroom. I just saying. Okay. Oh. All right, so let's see. I'm going to use this equation, and it's always the same. X equals -b over 2a. X equals -b over 2a finds me 2 things. It finds me the axis of symmetry, and it finds the x component of my vertex. Okay, so what is my b term? 8. So I have -8. Where did the negative come from? It came from right there. Over 2a. What's my a value? -2. So I get -8 over -4. Negative over negative is? Positive. 8 over 2 is, or 4 is positive 2. So x equals 2 is my axis of symmetry. X equals a number is a vertical line. X equals 2 is my axis of symmetry. Let's go to my straight. Yeah. Oh, yeah. So x equals 2 is a vertical line right here at 2. And I'm making it yellow and on the green, light greens for a reason. It's not the most important thing in the world for a parabola. It just exists. What else does that x equals 2 mean? Where do we start plugging it in? Where does it start going? Into the x of the what? not the equation, vertex. So I get 2 comma. I now need to figure out the y component. All right? So this is an x value. I'm going to take this x value, I'm going to plug it in there and there. So I get negative 2 times x squared, that's 2 squared, plus 8 times 2 minus 2. Okay? Let's see. 2 squared is? 2 squared is? Huh? 4. 4 times negative 2 is? Negative 8. Okay. 8 times 2 is? 16. And then minus 2. Okay, see if we can work this out. 8 minus 2, negative 8 minus 2 is negative 10. Negative 10 added to 16 is? 6. My vertex is at 2 comma 6. My vertex is at 2 comma 6. The yellow? I made it yellow for a reason. It's not the most important part of it. I'm just using it as a reference. That's the only reason why. I mean, I do what? Here, I'll do this for you, though, Armin. Let's see. I can do this, I think. Let's see. We might. Oh, yeah. Here, let's do that. Or, no, that. Is that okay? White?
That's even worse. Yeah.
Right?
See if you see the gun.
It's worse than yellow.
How about that? We'll do that.
That's good.
All right. I like it. All right. So my vertex we just found to be at 2 comma 6. I like it. I'm going to plug my vertex in the middle of my graph. Because the graph is symmetric, right? So what I do to one side, I do to the other. So let's pick one value bigger than 2. That would be 3. One value smaller than 2, which would be 1. Does everyone feel comfortable how I got that?
Yep.
I went one number to the left of my vertex, and I went one number to the right of my vertex. Yes? I think 1 is easier to plug into this equation. So now we're going to use this equation again. So I get negative 2 times 1 squared plus 8 times 1 minus 2. What's 1 squared? 1 times 1? 1. 1 times negative 2 is negative 2 plus 8 minus 2. Okay, negative 2 added negative 2 is negative 4. 8 minus 4, 4. If this is 4, then this is 4. All right? It's symmetric. Okay, let's see. I got 1, 4. So 1, 2, 3, 4. And 1, 4. 1, 2, or 3, 4. Can you start seeing the shape it's going to start taking? All right, let's find another value. I think we could do this. Okay, let's go one number this way of 1. That gets me to 0. Let's go one number this way of 3. 4, yeah. 0 is easier to plug in than 4, isn't it? But it's going to be the same value, which is really great. Plug 0 in. Negative 2 times 0 squared is 0. Plus 8 times 0 is 0. Minus 2. 0 plus 0 minus 2 is how much? Negative 2. That's negative 2. That's negative 2. 0, negative 2 right down here. 4, negative 2 right here. Ladies and gentlemen, let's see. Let's pick that color. That'll be all right. Ladies and gentlemen, does this cross the x-axis?
Yeah.
Can I see exactly where it's crossing the x-axis? Exactly where? Or somewhat where? Close to where? Somewhat close. So I can't see exactly, right? Okay, cool. So my y-intercept, hang on, let's figure it out. What's the y-intercept? The y-intercept is where x is 0. What's my y-intercept?
0 minus 2.
0, negative 2. Good. My roots take place here and here. Right now, I'm going to say that my roots are irrational. My roots are irrational for this reason. I can't factor that. That would have been prime if I factored it. But the solution to this problem, to find out where it's equal to 0, happens here and here, right about. Do I know exactly where? No. Do I know pretty close? Yes. Yeah.
It's just a graph. Is there a way to do this on the calculator?
Oh, yeah, baby.
so that's.
All right. Give your book.
Mister, if you have a calculator, you can just put y equals 3x squared minus 12x, right?
Yeah, but I don't need technology to think on me all the time. I like to think on my own. I like critical thinking skills, and I know you do too. All right, guys and girls, try page 77, 78. Try it. Try it. Try it only.
How we do?